Can hear? Good afternoon, everyone. Seventeen student only, or maybe 17. 18. So today I will cover the searching algorithm, and finish this. I think Monday already cover the binary search, and then today we will cover the key things, which is the hash table, which can further improve the searching, by hashing. Then next week we will start the graph. Well, week 10, 11, 12 will cover the graph for over 3 weeks. So that's when graph is one of the important topic in this algorithm part. Okay, then assignment 6 will be released probably later. After the class I will do the invitation, all this. Okay, and the deadline for the assignment 5 is next week. Okay, and also take notes, don't try to do something funny in the platform. I think some people go and change this and that. Later we can't find your submission, you need to take the full responsibility. It's you yourself go and, just like exam, you don't want to fill in your name, you don't want to write your metric number. You need to take the responsibility. You don't come and claim that you did submit, just because you go and play the something funny. We will just assume you didn't do any submission. So just take notes. And I think common question asking whether can I declare some small function to help me, assist me to solve the problem in the assignment. Yes, for me, I allow. Okay, as long as the function you declare is not trying to cheat the system or trying to make the main program not working or in whatever form, then I'm allowed. But or whether you can use some library. Someone asking, as long as Hacker Earth let you use it, I basically allow, but I'm not encourage you to do it. But I won't penalize you. But I just like I would say that maybe today is working. Next time I cannot guarantee some other library will it work, because some common question is like you are trying to use some function which is not the standard built-in function. That means it maybe can find that function in your IDE, in your platform, but you cannot find it's not a standard one. Actually, it's not the so-called the C standard library. Actually, if you go and online search, certain function is not the standard built-in function. So of course that one not surprising. When you submit, you don't need to ask me whether you submit. Actually, they basically quite strict. The platform actually they quite strict on those. They didn't put those non-standard library in the system. So not surprising, definitely cannot one. Someone asking whether need to submit the assignment to NTU Learn. No need. For me, I don't need, I'm able to find out all your submission. Yeah, so that's why I said you don't have to, and also don't try to do any kind of a cheating. Same thing. If you didn't get caught, you are unlucky. If you are lucky, you get caught, 0 marks. Okay. So yeah, just another thing someone asking is like, okay, someone asks whether, okay, this slide I already uploaded in the NTU Learn. So you want, you can tag it. But I would say that the notes I uploaded earlier is already there. Yeah. It's already all the material I want to set is there. This is just assist me to do the lecture presentation, all this. Yeah, so may not be in the full details, and a lot of things overlapping and repeated. So yeah, but someone still want, yeah, well, I just let you decide. You yourself judge which one is the one. Okay, so I just simply put on the NTU Learn. Yeah, you yourself judge whether you need it or not. Yeah, personal opinion is maybe you don't really need it. Yeah, no point to repeatedly read the same thing. And again, if you read this thing 1 time, 2 times, don't understand, watch a video, still don't understand, you probably need to seek for some help from some consultation. Okay. I think what else I need to set? This one, assignment deadline. Okay, oh yeah, one more thing. Okay, I think during the tutorial, maybe someone asking the big O. I should cover the big O first. Maybe add one more empty slide first. Okay. Then, okay, someone asking what is the, yeah, big O, want to clarify something like about big O, big omega, and big theta. Okay, first, I think this week tutorial quite a few students asking how do we select this. It's not really this thing is for what someone thinking is like this one is for worst case, this one's for best case. Not true, not correct. Best case, worst case, or this is the average case. Not this. I don't know where you got this. I don't think I talk about that. Yeah. The thing is like that. Okay, today think about it. Why you need this asymptotic notation? Why you need to know this? Why people define this? The thing is like that. Today I have an algorithm. I'm trying to do the time complexity analysis, and I come out some result. And then I want to describe this result. How do I describe this result? I got some algorithm. Yeah, doing something funny. Yeah, this and that. Yeah, then run a for loop and maybe some recursive function, X, Y, Z. Yeah, something like that. Yeah, whatever lah. Yeah, so after I analyze it, the time complexity is maybe n squared plus some time comparison or whatever time complexity. Okay, is maybe n plus log, and maybe I have this algorithm in this time complexity. Yeah, so I want to tell people that how good, how bad about describe this time complexity. There are a few scenarios. Yeah, first people just want you to describe what is the time complexity. Maybe this is after I analyze in the worst case scenario. In the worst case scenario, I have something like this time complexity. My time complexity is in the worst case scenario. In the worst case scenario is something like this. Then what is the time complexity of this algorithm in the worst case scenario? So since I'm very sure that worst case scenario is this particular time complexity, I'm very sure, yeah, cannot be other part, in the worst case scenario, cannot be other things already. Of course, more precise asymptotic notation representation should be in this way. Yeah. Of course, you can say that you can write in this way. It's equivalent. Is correct. The statement is correct, but you can simplify it based on the asymptotic notation, the big theta or big O or big omega, same thing. I can simplify to this simple form, clearer, very clear that this is a quadratic function. Quadratic complexity class is quadratic class. Then of course this is the better representation. Although this statement is not wrong, but it's not clear that whether you really know what is the asymptotic notation. Okay, the statement is not wrong, but not clear to showing you that you understand what is the asymptotic notation. Okay, and then of course people were trying to say that, I also can write this way, what? Yeah, yes, you can, but this representation, you showing me that actually you're not too sure what is in the worst case scenario. You only think that worst case scenario is not worse than this n squared. This statement not wrong, but incomplete, because you're trying to show in big O notation is trying to say that this thing can be better than that. Maybe worst case scenario somehow can be constant time. In your this representation, you present is trying to tell me that in the worst case scenario, it can be constant time, can be linear times. You're not sure. So of course, if this representation compared to the first one, of course the first one more clear, complete, better lah. Yeah. But today, if it's another way, I'm not asking you the worst case scenario. Maybe they just want to know how is this algorithm. Yeah, you want to describe about this algorithm. Then, yeah, you only analyze the worst case scenario, and you have no idea how good it can be. Or maybe you also find out that, but it's in a range from constant time to quadratic times. Then the better representation about this algorithm overall, in all the scenario, overall, is big O n squared. So that is like using the big theta, big omega, or big O is the way you're trying to express your understanding about this time complexity, the order of growth, the asymptotic notation. In asymptotic notation, to describe how much you understand about this algorithm. About its time complexity of this algorithm. So you need to decide what is the best, most appropriate notation for you to answer the question. Although all are somehow equal, can accept, but the information, your this description, you use the big theta and big O notation. You are trying to describe different things. One is you very sure that you are tightest bound. If it's in a big O, you only tell me is bounded above by some n squared. The order of growth, is bounded above by this n squared. But you have no idea how good it can be. Maybe it also can be linear. Maybe it also can be constant. In your this expression, you didn't tell me about you really know that it only can be n squared. So that is how you select whether in practice point of view how you select big theta, big omega, and big O. Okay, so why online you search here and there, people when they talk, a lot of time they only talk in big O notation. The reason is very simple. A few. One is the person really don't know anything about big theta and big omega. Secondly, because I just want to, I'm not talking about in worst case or in average case or in best case. I'm talking about general, about overall, about this algorithm. Yeah. So when I want to talk about this algorithm general, and a lot of time this algorithm range from best case to worst case. There's a range from linear to quadratic, or maybe from logarithmic for or constant time all the way to quadratic. I can't write one sentence, one notation to the only one notation I can use is big O, and tell you the worst case. Yeah, it's better than I use a big omega and tell you that big omega constant times. Yeah, which one clearer compared to I write in this way. Overall, this algorithm is big O n square and or I said big omega 1. Which one can tell you better about this algorithm? Yeah, to give you better understanding about what this algorithm look like. How is the time complexity about this algorithm? So therefore, people usually use big O instead of. You very seldom see people use the big omega. Big omega showing that the thing cannot worse than that. Yeah, especially then what happens is like big omega constant time. Yeah, cannot worse than that. But how cannot better than this. Sorry, should be cannot better than this time complexity. But how worse it can be, you have no idea from this description. Yeah, then I really don't know should I implement this algorithm or not, because it only tell me it's in constant time. Okay, isn't big theta the best represent then? So that's why I said that when I talk about general, the whole algorithm, they got best case, worst case, and average case. I only can write in one sentence, one notation. You only can choose one notation. You can't use a big theta because there's a range from best to worst. Yeah, but today if you only talk about worst case, only one case, only one scenario, then of course you can use the big theta. Because I know exactly, unless that one case also got a range. If that case only got one time complexity, very clear, is the time complexity, then I describe order of growth, then I can just use the big theta when I only talking about one scenario. But if you talk about the overall, when you trying to describe, is about the overall, the whole, all the cases, all the possible scenario, then a lot of time you find that you very hard to use the big theta because there are too many scenarios in that particular algorithm. Then maybe use big O is better. And that is why you commonly see people use big O. Yeah. I hope you all clear about this, because quite a few students asking me during the tutorial class. Okay, back to where we stopped last week. We stopped at here, that the binary search, after we analyze, we find that the average search, if comparing two algorithms and they have the same rate of growth, it is safe to say that one is in big O of the other. They have the exactly same order. Yeah, the order of growth is the same. If the rate of order growth same, I think both of them having, to more precise, they are each other. But it's a bit weird that to set the time complexity A is in time complexity B. Yeah, what are you trying to describe? Because big O, big theta, big omega, three of them are in the same, are talking about a set of function. So I can't say is it safe or not. That statement may be correct, but what do you want to deliver? What do you want to tell people about that? It's like A is in the time complexity A is in big theta of time complexity B. Yeah, this description, I don't know what does it mean. Yeah, so that's the thing lah. Okay, so back to this. So average case, you observe. I think you just use one example. I think Monday already show you that. Yeah, you will find that among these only the middle one have one comparison, one case only. Yeah, then you find that there are two cases. Yeah, there are two positions require two comparison. You also can see here and here and here. There are four positions require three comparison. So if you extend this, you can observe that always you got one position require one comparison. You have two position require two comparison. In the binary search, you have four position require three comparison. And not surprising that the last one is 2 power to t minus 1 require t comparison. Yeah. And then you have 2 power to k minus 1 element. Among them, one position is one comparison, 2 require 2. So you have 1 require 1 comparison, and you have 2 require 2 comparison. You have 4 position require 3 comparison, and then you have 8 position require 4 comparison, and so on and so forth until 2 power to t minus 1 position require t comparison. Yeah, so that is the summation of this thing. So everyone is like t, then you have 2 power to t minus 1. T can be 1 to k. Then you have t comparison. So all this is a total number of comparison among every element. Yeah, total, sum it up. Yeah, sum up all the, this is how we express in summation form, of this series. And then let's say each position have equal chance to be searched. Then equal chance, that means you got n element, so it's 1 over n. The probability for each cases is 1 over n. Then this one, the summation, I already told you that it's inside the max revision notes. Yeah, okay, the proof I'm not going to go through. But you'll find that this week tutorial question 3b, question 3b, that one also have the similar case. Yeah, you will find that all these things got one common thing is like, they got one is a arithmetic series. They got another term, another one is the geometric series. Yeah. So it's a combination of the arithmetic and geometric into one series. To resolve this thing, I already showed you the trick behind. Actually, it's just multiple the series by 2, then you subtract the second one to the first one. Then then the middle will come out, all become the arithmetic can be somehow removed, then become a geometric series. So after you do this summation, then this one you substitute back. Then k, I need to bring everything in terms of n. So this one you can from earlier assumption, you can find out that k is log 2 n plus 1. Okay, then you just substitute into this equation. Then you simplify it. Then average case. So overall average case, success. Just now the one is a success one. Of course, you need to consider there's another case is unsuccessful case. That means the key is not inside the array, in the array. After you binary search so many times, this is the successful case earlier. Where is it? Should be, when I do this worst case, that means unsuccessful case is the worst case. You got the worst case. This is the worst case. Worst case is this one. Worst case is here. Okay, so then this is the other cases. Successful case. All are successful case. That means the key is inside the array. You found that is also another logarithmic. Then you combine. Successful one is this one. Then unsuccessful one, average is this one. Unsuccessful, all take the log 2n plus 1. Successful can be a lot. I mean, average out is this. Then you need to further taking this. You have a probability successful, then an unsuccessful search. So, well, after this, you can see. After I simplified this equation, this term, you can see that this Q definitely less than 1. Q is the probability, definitely less than 1. Okay, that's one thing. Secondly, this term, is a very small. Very small. When n getting bigger and bigger, not surprising, log over n will be getting small and small. So that's when this thing not important, this thing not important. The most important is the first term. So that's why binary search, actually intuitive, you also expect that is the things. It should be a log 2n plus 1. Comparison on average for any n entry. So that is the average time complexity of binary search. Okay. So earlier we already introduced the linear search. Linear search take all n. Then binary search is logarithmic, improve from linear to logarithmic. If we want to let it search even faster, are we able to do it in the constant time? Because after linear logarithmic, next one you want to achieve, of course, is a constant time. Then searching in constant times, is it possible? Technically, somehow you can. That means what you can do, that means you need to use a lot of space, to improve your time complexity. But doing that means your space complexity probably will increase. So there's a way which is using hashing. Hashing is a way to further improve the search time from logarithmic to constant time. But the drawback is your memory need to increase. You need to use a little bit more memory. Maybe a little bit more, maybe more. Depends how you design your hash function and how you handle the collision. So this part we will cover what is the hashing, what is the hash function, and how do we handle the collision, and what is collision, and how do we handle the collision. There are a few approaches. And then, of course, we need to consider in the implementation, you can insert, of course, you need to consider how to delete a key from a hash table, and so on and so forth. So, what is hashing? One way you want to get the thing constant time. I think you give me the key, search it. I immediately tell you that yes or no. So one not smart way people can think out is like, let's say today your search key is all integer number. Okay, very simple. I just create a super large integer array. Super large integer array. Very large. I don't know what is the maximum. It should be 2 power to 8 by 16, is it? 2 power to 8 by 864. 2 power to Yeah, should be 2 power to 8 byte. What is the maximum? You can search what is the maximum. Let me make a quick search. Forgot the number. Keep first. Okay, let me make a quick search. Maximum in integer in C. As said, the maximum is unsighted integer. Maximum is 42949679295. Okay, this is the maximum. Okay, then I create a 4 million, I don't know how many. Yeah, 42 something, the array. Yeah, so maybe I only store 10, 2 power to 32, thanks. Yeah, 2 power to 32. Yeah, let me recall why it's 2 power to 32. Yeah, 429496. What is it in 42 million? Billion? 42 billion? Yeah, something like that. Array. And then I store 10 number. I store 20 number. I store 100 number. So let's say 1, I store it here. If it's 1, I store it at the index 1. Yeah, if it's the 9, I store in 1, 2, 3, 4, 5, whatever lah. Maybe a lot. In billion. Then and now you only use 10 memory location to store the actual number. The rest unused. Yeah, because you only store 10 number. The rest unused. Then when you search, you tell me you want to search whether 9 is inside your data or not. Yeah, I just simply go to that location. Tell you that yes, yeah, inside. Yeah, when you want to search 3 whether inside or not. If 3, I go to that array, is showing somehow empty. Yeah, then I tell you no, the 3 is not inside. Yeah, so almost instantly. But the drawback, very obvious. Every time you need to create a super large array, 2 power to 32, yeah, element array, just store a few number. Yeah, so it's just something like this. Then you have you know the search space, the universal key, all the possible searching key. Yeah, then you create the corresponding array. Then you only store a portion. Yeah, a small portion is with the actual data. The rest left it as unused. Yeah, so this is so-called direct address table. Yeah, so yes, you can reach the search time is constant, but the array size, if you need to solve certain problem, you need to create a few times of the array. Then that memory storage is very huge. In fact, in practice, very likely you can't create it. Yeah, 2 power to 32 array. I think you can go and try and create it. Normally, you will return some error. Yeah, probably the computer not able to allocate such a huge memory location for you. Yeah, because usually the search space is much larger than your actual store data. So that is not a very practical way to achieve constant time. So people start thinking, yeah, since this thing is just a mapping, I just you give one key, you map to certain location. Yeah, direct address table, that means direct, is just you give me a key, I directly map to the corresponding index. So yes, very costly. So can we reduce the array size? Yeah, then people come out an idea. Yes, I use the hash. I can declare a function, some function to do mapping, to make this 1, 2, 3, 4, 5, this 5 number map to a smaller array. Maybe the array, the size is at least need to 5 lah. Maybe 10, maybe 20. Yeah, I just design a function. Because all this is just a mapping. So I just design a function. Yeah, which can map the key to certain index. So when you search the key, I just apply this particular mapping function. I can find out the corresponding index easily. Yeah, and then search it. Yeah, so that is how the hash function come out. So the purpose having the hashing is like they want to reduce the key search space, the key space to some reasonable size. Depend your application. Okay, each key, and then this function definitely is unique. You will map to the corresponding unique index. That's mean next time you want to search, I apply the same function. They will give me a unique same index to search the corresponding key. And doing that, of course, this is just apply a function. So that function should be very simple, easy to compute, that to keep the complexity remain as a constant. So the complexity still remain as a constant on average. So that is what we intend to do on this particular mapping function or hash function. So then this smaller size array will become, we call it hash table. So difficult to write. Hash table. Okay, hash array. Okay, then the mapping function called hash function. Whatever. Then the slot, each slot, I name it as hash slot. Okay, then of course you find that this one definitely got problem, because you trying to do the mapping to a smaller size. Definitely somehow there's a chance that this mapping will let two different key map to the same place, map to the same hash slot. Then that will causing the collision. Multiple key are mapped to the same hash value, hash slot, then the collision occur. So there's a problem. So here you can see there are two problems here. First, I need to design a hash function so that I can map my all the key to the unique index. No matter how smart you are, no matter how you design, this one is like, you have so many keys, you map to a smaller array. So definitely there's a collision. So two things we need to think about it, how to design the function and how do we handle collision. We design the function, yes, we want to minimize the collision, but no matter how smart you are, the collision still will occur. We still need to have a plan to handle the collision. So that is something we need to think about it here. Then, if there are n record stored in the hash table with a hash slot, so the here we need to know this definition. So the log factor is known as, I name it, or some book name it also, call it alpha. Is the number of record over h is the slot. That's the log function. So to tell you that how many slot is already occupied, and you still have how many slot is free to use. And not surprising that you find that when your log factor is increasing over the times, you insert more and more key, the probability collision occur is getting higher and higher and higher. Starting, of course, first time you insert the very first key into the hash table, definitely no collision one, because totally empty, no collision. But when you insert 2 key, 3 key, 4, 5, 6, 7, very soon you will realize that collision will occur soon. Even you design a very good hash function, to minimize the collision. So back to the hash function. So a few things we need to consider. So this hash function, must be able to map to all the possible value, in the hash table, and uniquely. This is the one of the criteria. Of course, one of the criteria. You want to fully utilize the hash table. Of course, you need to make sure that your hash function able to map the key to all the possible. There's all the hash slot have a chance to be mapped, and yeah, some value. Otherwise, you will waste the space. And must be unique. That means this time A map to this location. Next time you trying to search A, yeah, using the same hash function, you should get all the unique mapping. Otherwise, your searching will be very tough. Or not possible work, right? So this is the criteria, having the right hash function. And then also we need to make sure, or we try to have the hash function to make the key evenly distributed, because we don't want them to cluster in one certain location and then the other side seldom use. Yeah, so we hope that they can evenly distribute. Every slot have an equal chance, yeah, can evenly distributed all the data, even all the key evenly. Then that will be also reduce, yeah, the one achieve what we want, minimize the collision. Yeah, and moreover, your hash function must be easy and fast compute. Yeah, usually must be in constant time, regardless your problem size. Your problem size big or small, yeah, must be let the function easy to compute. Okay, answer a few questions here. Alpha equal to 1 is best or worst scenario. There's no, cannot set best or worst scenario here. Alpha is like over the time you insert the key, getting bigger and bigger. First, equal to 1. Later you will find that not, yeah, sometimes it can more than 1. Yeah, depend how you design your hash table. So it's not best or worst issue. It will yeah, that is one of the factor lah, but the problem side still the end lah. Yeah. Then why the search not big data? Yeah, because yeah, later you will find that yeah, the like I said earlier, the overall the search time general, I'm not talking on particular case, worst case or best case. So I only can set that overall this search, this algorithm, this search time, yeah, is in constant time. Yeah, you if I set big theta, actually I also can set, because definitely constant time on average, maybe yeah, I think I can set so, because it's a constant time. I cannot get anything other than that, right? Yeah, I think yes. I think I said so also fine. Write it in the big theta. Sound better. Okay. Yeah. Okay. I think yeah, you are, I think better. Because I cannot, as I said, I cannot find anything else, right? I wish always. Yeah, but it's not all, yeah, on average, if I said on average, yes, I should set big theta, more precise. You are right. But if I said about this algorithm, then maybe it's a big O one, because in certain circumstances it's not in constant time. Yeah, some circumstance, some scenario, that's in so-called the worst case scenario. Yeah, it may not be in constant time, and very likely you can't find the thing and the table is full. Then you will take linear time to search, because after you search through every element in the table, you still cannot find the object, you still cannot find the key. Yeah, then that will be linear time. So yeah, and that circumstance is in linear. But we try, when we design the hash function, we try to minimize such thing happen. Yeah, although such things still can happen, we need to design our function to reduce, to minimize such thing, because we don't want, today we use the hash table is because we wish such thing not happen that frequently. Yeah, so on average it should be constant time. So there are a few ways to achieve the hash function. Yeah, there are a lot. Actually, this here I just give you some example. Yeah, there you can use your innovative idea to create anything, as long as you make sure that you fulfill these few criteria, yeah, those hash functions should be okay to use. Yeah, so here just briefly tell you a few. One, which is quite commonly used here and easy to implement. One thing is very easy to implement is take the modulus based on your hash table. If my hash table got 10 elements, that means after I modulus, the possible index, yeah, is 0 to 9, right? So just nice that I can use it as an index to do the mapping directly. So this one is commonly used. Use the modulus. But these things, when you apply it into the real data, yeah, normally in the real data, we will suggest use the rule of thumb or something like that. People will suggest is like we trying to select the hash table size in prime number. And also this prime number, try not to too close to any power of 2. For example, this number may be not a good hash table size, 31, because it's quite close to 32. And also we try not to, yeah, in fact you can use any number, but why they want to set so, and why they want to set that, why trying to set that we should avoid to using power of 10. We should avoid to use the power of 2, because in our daily life, a lot of real world data is not really random. It's not really random. And for human one, maybe you stay in hostel. Yeah, your hostel, yeah, 1, 2, 3. Yeah, your room is room 1, room 2, room 3, or you stay in HDB block. Yeah, or your street name, yeah, maybe it's Avenue 1, Avenue 2, Avenue 3, and so on and so forth. Maybe there's no Avenue 9, Avenue 8. Yeah. Maybe, yeah, there is an Avenue 1, maybe there's no Avenue 8 and 9. So statistics found that 1, 2, 3, 4 appear more frequently than 8 and 9, right? So that's why they are not evenly distributed. So when you're trying to use the decimal number 10, 100, a lot of time you will end up that your data trying to store everything in slot 1, slot 2, and slot 3. Instead of then slot 8, 9 will seldom use. So they are not evenly distributed. And why not power of 2 or close to power of 2? Because in the digital world, a lot of things in digital then is another way. Power of 10 is human, because human got 10 fingers, so we use a decimal. Computer only have 2 fingers, 0 and 1. So a lot of data is stored in digitally. Then they were trying to in related to power of 2. Then it's very easy to end out that your data also have the issue when you store your table size is close to power of 2. Yeah, they're very easy to have certain slot have higher frequency to be mapped. Then other slot may be seldom used. So that again breach the earlier requirement, evenly distributed the key. Yeah, so that is something when you use this on the real data. Yeah, we suggest that using a prime number but not too close, because prime number, yeah, you'll find that they usually they will. So in other words, when you use all these functions, sometimes you need to have some knowledge about your data, how well it distributed. Yeah, so folding partition the key into another way you can use the folding. Basically this one is like you got maybe your phone number, 987 1 2 3 4 5, maybe, I don't know. You want to make this thing to, you can use 2 large number. Instead of using modulus, you can use partition this, partition in whatever partition, and then do some divide the key and then combine it, whatever you can invent. Then it's a so-called sheet folding. In the end you get a index, then you map this number to that particular index. Sometimes it's like just no reason, just anyhow people trying to design a function on it. Yeah, as long as you can evenly distribute the key, yeah, not make it cluster into particular area or make certain slot highly used, so it's okay one. Yeah, so that is one way. And some people maybe can square the number. They don't want to use the last few bit, then they're trying to square it, then take the middle one as an index also can. Yeah, some is using this multiplicative quadrature method, which is actually this one also used for generate our compute. One of the method we generate the random number in computer, pseudo random number. Yeah, so basically you can see that using this example, this is just one of the example. Yeah, you can see my 1 will map to 13, 2 will map to 26, 3 will map to 8, 21, 3, 16. You find that there's no, it's look random. Actually, they're not really real random lah, but quite close pseudo random lah, I would say, the mapping. And you can easily use this mapping function to find out. Although from what you see, look like the mapping is like a random, but actually you can use the formula to find out the corresponding key. Yeah, so some people may use this way. Yeah, these are all the options, and you can think other way. As long as fulfill this field, you can map all the possible value within the range of the table uniquely. Secondly, the mapping should achieve an even distribution of the key, and then the function is easy to compute and fast in constant time normally, and you can minimize the collision. This can not really you have to use the particular one, but here I think normally I trying to use the first one the example I show. Because this is not the part I'm interested to discuss what are the function, what is the property. This is more like a function, is in mathematics how you design the function, the mapping function. So I just simply choose, normally I think in the example and assignment, all this, I trying to use this first one to work on it. So no matter which function you choose, how smart you are, are any of these mapping unique? What do you mean? How are any of these mapping unique? So each number mapping unique, that means 1 will mapping, like here, this one will mapping to 13, for sure one. In this, that means your this function only can let 1 map to 13. When you give me 2 will always map to 26, so-called unique. But there's a chance, that means this thing, there's a problem, is like, so no matter how you do, definitely in this case, you're not surprised that 16 will map to somewhere, then collision. That means you got multiple number maybe map to the same slot. Then that is so-called collision. Because you got so many search key, you got 100 of search key, your table is only maybe 30. Definitely got 2 key or 3 key are mapped to the same slot. So if one key is already insert and occupied that particular slot, another key trying to insert into the same table, collision occur. Then that is the next question we want to discuss. How do we solve this collision? When one key already insert to the hash table, another key through this hash function, they give you the same slot. They indicate this particular key also have to insert into the same slot. But this slot already occupied. What can I do? There are a few ways. One is the closed addressing hashing. The other one is open addressing hashing. So closed addressing hashing, very simple. If they collision, right? No, then okay, fine. I don't store it I create a hash table followed by a linked list. So there's no collision issue. Every time you insert 84 into this particular slot, Next time you want to insert 39, fine, I just create a linked list. I just add at the back of the 84. So instead of store one number, my slot, instead of store one number, my slot, I use it to store a linked list. Then I can insert arbitrary size. Yeah, you got 10 key have a collision, just insert at the back, no problem. Yeah, so that is one way to solve the collision by clustered address. So-called clustered addressing, that means the location is fixed, is clustered, is fixed. So once you do the hash function, you do the calculation, the key is insert to the I slot in this location. Yeah, you won't change. This address definitely got the key. Yeah, they will put in the same location, but using the linked list to store. So that is so-called clustered address, or some call it separate chaining. Yeah, the change. Yeah, like a change. Yeah, so you're adding more key, then they just add at the back. No problem. You got how many key? Got collision. I can just keep insert it endlessly. Yeah. So the key are not stored in the table itself. Yeah, you create a linked list to store. So during the search time, the search key, the search element with the hash address I is compared with, so you need to search. When you search, the thing was we search, when I want to search, for example, 92, then you apply the hash function. The hash function will indicate you to go to this particular slot based on the given 92. Then they will start searching. That one is just like a normal linear search. So in the closed address hashing, there will be alpha number of element in each linked list on average. Correct? If alpha is just now I already mentioned, alpha is the log factor n over h. So on average, if the hash function can evenly distributed your key, evenly distributed your n. So on average, each linked list only have, on average, each linked list have alpha element. On average, if they can evenly distribute it, so on average should be in alpha, right? So the search, so worst case, average is alpha. So now the next is like, what is the worst case scenario? What is the worst case scenario for closed addressing? So not surprising, unsuccessful search, just like normal linear search. Just like any normal linear search. You take big theta n. Then successful search. What is a successful search? So what is the, first, what is the worst case? What is the worst case? So that means I have a hash table. The worst case, I have this kind of scenario. Is the worst one. All my key, worst case is like that. All the key, I don't know why, so unlucky that all the key you want to insert all squeeze into the same linked list. That is the worst case, right? Then that end out that, your successful case and unsuccessful case, all the process you search in the worst case scenario will be just like linear search, because actually you construct is a linear. It's a linked list, just a normal one linked list only. So every time you search through this whole linked list for all the data. So that become your time complexity. Become always big theta n, just like linear search. Okay, just like any sequential search or linear search. You learned earlier. So this is the worst case. Then what is the average case? Average case, unsuccessful search. Average, that means average. What is average? By right, that this kind of case, this kind of worst case should not happen frequently or rarely happen. I would say. Normally, if my hash function design well, it should be trying to an average should be evenly distributed my key. Maybe someone got this, someone got 1, someone got 2. They evenly distribute all my key into different slots Okay, let's say my slot is evenly distributed. Then unsuccessful search, you will take average of alpha. You go to any slot and then search particular key you are looking for. Then you will take alpha key comparison. Yeah, because on average, each slot have n over h key there. So not surprising, you will do n over h key comparison. Okay, yeah. So that is the unsuccessful. The key is the next one. Okay, pay attention. Successful. How about successful search in this? Yeah, how to calculate the successful search? Then you need to imagine that. It can be a few. So today, if I have in this one, maybe a little bit more. So I want to search what is the when it is a successful search, what does it mean? Successful search, that means you search the key, can be the first position, can be in the second position, can be in the third position. How do I calculate the average? So the idea is this. Imagine that you haven't searched the thing. So how many items do you have? So if you have so if you are trying to search can be first, can be second, can be third. So you can be before the you need to imagine that before the I item is inserted into a hash table, this I item is the one you want to search. Imagine that this particular item is not yet inserted into the hash table. So in your hash table, you have I minus 1 item. I minus 1 item. Okay. The table size remain unchanged, of course, is h. So average length of the linked list, each linked list is I minus 1 over h. Correct? Okay. So when the I item is sought for, the number of comparison is, on average, you will do I minus 1 over h unsuccessful search first. Because the I1 is the one you want to look for. So first, you need to go through, on average, you need to go through I minus 1 over h unsuccessful search. And then you search the item, the I item, you search it. So that is the number of search on average the required search you need for I item. Then the I item can be first, can be second, can be third. So on average, you got n item. You can search a first item, you can search a second item, you can search a third item. So you got so many combination. Maybe clean it. So on average, can be the first item, can be second item, can be third item being searched. So to n item. And then each item got equal chance. So this thing is the summation of 1 plus I over minus 1 over h. So you can try to simplify this summation. So this one, the first term is n times. Then the second one is 1 over h, is nothing related to the I. So I is here. Then this one is the arithmetic series. So this one got n. This one should be n. And then plus this part, 1 over h. Summation. So this one is start from 0. The first plus 1 plus 2 plus 3 ... to the last one is n minus 1. So you got how many? You got n term over 2. The first term is 0. The last term is n minus 1. So the summation of this summation, this thing actually is n over 2, n minus 1. Then n times h. So overall, this is the average number of key comparison, the required key comparison. So this thing, the average time complexity is big theta 1 plus alpha. This one, n over h one, you notice? Yeah. Or alpha also can. Yeah. The purpose I put 1 plus alpha, showing you that there's, is first you go through I minus 1 over, you need to go through I minus 1 over h plus one more. You always need to take, you search a thing, the last step is find that one. Yeah, you found it. Okay. So n is less than n. If n less than h in this average case, then alpha is the log factor. So it depends your data over h. Yeah. So if I think you're trying to set is not the if n is proportional to h. Yeah, so if n is proportional to h, then you can conclude that this thing is in constant time. Because if it's proportional, then this thing is in the same order of growth, then all this thing is just a constant number. All of them are constant number. Everything, I should not cancel. Everything is in constant number. Yeah, so constant, then this thing can be taught in constant. So the average time complexity of closed address hashing is still a constant time. That's what here trying to set. Because here we trying to talking about average case. In average case, your key should be equally distributed on average. Yeah. Earlier slide I show you is in the worst case. In the worst case, you consider the worst scenario. Yeah, that means everything squeezed into one slot and then into a super long linked list. That is the worst case scenario. But normally, it should be, on average, it should be evenly distributed. Like earlier I said, the hash function should design to make it evenly distributed. Okay, so searching take constant time average. On average should be constant time. Okay, well, that is the closed address hashing. I think I have to quickly finish the rest. Okay, so this is a closed address, but you need to create a linked list. So that is the something we maybe we don't really like. How people think another way, which is open addressing. Using open addressing, that means I open my address. The location is not fixed. What happens if there's a collision? Then I will trying to find alternate slot. If the collision occur, I will trying to find the alternate slot. Yeah, I'm trying to find another free slot. Yeah, this is the open addressing. That means the addressing is free and it's open. That means this address is not working, it's occupied. Collision occur. I just look for alternate slot. Okay, there are a few ways to find the alternate slot. First is the linear probing. Linear probing, very simple. If this slot is occupied, then I just simply find the next location. I just find the plot the next slot and check whether it's occupied or not. So basically, it's trying to k plus I modulus h. Yeah. So the I, of course, must be, you don't have, you plus one. Yeah. You, for example, okay, first I need to insert something first, then the collision will occur. Then this one, I just simply modulus to 7. This table got 7 slots, so I just simply modulus 7. I can insert. Initially, no collision, no issue. Yeah, 11 modulus by 7, collision occur. Yeah, when the collision occur, linear probing, very simple. This slot is occupied. I just plus 1 modulus, so will be 11 plus 1 modulus 7 will be go to the next location. Yeah, unfortunately, this location also occupied. So, no choice, just plus 1 more 1. Then got 11 plus 2, modulus by 7, plus 1. This location still occupied. Then plus 1 again. Yeah, then this is so-called linear. So you can see that you just move one by one by one. When you reach the bottom, you will back to the first slot and then carry on to search any available slot. Whenever you find a available slot, you just insert it. Yeah, so this is so-called linear probing. So this one, what is the issue? Very soon you will realize that all the key very easily squeeze into particular cluster. Yeah, that is so-called primary clustering. Yeah, this will increase your average search time, because every time you want to search 11, when you want to search 11 in this hash table, you will search this one first, followed by this one. Not here, not here, then you found the key. So you will end up that you need to do 1 key comparison, 2 key comparison, 3 key comparison, 4 key comparison, then you found the 11. Yeah, because of this primary clustering. So linear probing, people find that not very good. Got this primary clustering. So people think that linear not working. How about quadratic? So someone invent the quadratic probing. So quadratic probing will go to square. So they, instead of plus I, they come out plus I, C1 plus I plus C2 I square. Yeah, modulus H. So C1 and C2 are some constant. Here, maybe use example, illustrate. Let's say I choose H equal to 2 power to n. C1 and C2, I make it as half. So let's say I have a hash table 2 power to 3 lah. 2 power to 3, you got add element. You got add hash slot. So based on this formula, you expect that you will move your plus 1, plus 3, plus 6, plus 2, plus 7. Yeah, not in linearly. Yeah. So how does it work? Okay, starting definitely no collision one. So everything can easy insert. Yeah, starting no problem. Insert here, insert here, insert here. Okay, again 11. 11, I mode 8. I will get 3. So I will trying to make this thing insert 11 to hash table 3. The hash slot 3. Yeah, but it's already occupied. So the next location plus 1. Yeah. So plus 1 will be 11 plus 1 mode 8. Yeah, but also occupied. So I wouldn't plus 2. This time I will plus 3. So I will 11 plus 3. I will go to this location. Yeah, just nice that there's no, it's empty. So I insert it. So through this, how many key comparison? 1 key comparison, 2 key comparison, I save 1. I directly go here. When I said key comparison, that means there's a key inside. Then you can compare. So I call key comparison. Okay? So when there's no key comparison, here there's no key comparison. I already insert it. So 11 is here. We'll insert it. Okay? So that's, you find that you only search 1 time, then you jump 1 time, you find the key. So this one seems like the problem is solved, like just now the clustering, but actually it's not true. You will find that as long as you're trying to insert the key to the slot 3, maybe other number also need to insert to the slot 3. Yeah, then occupied, you always will go through this location, go to this location, go to all the same pattern in this sequence. That is known as secondary clustering. If 2 keys have the same initial prompt position, like 3, their prompt sequence will be the same. Yeah, this will form a kind of a clustering. Also, physically, you look at it, there's no clustering, but actually there's a form of a secondary clustering. They will always jump into the same hash slot and check and do the key comparison and check the availability. So sound still not good. Yeah, soon another person will propose called double hashing. Yeah, double hashing will be a little bit better or much better. It's a kind of a somehow random probing method. You got 2 hash function. Yeah. Okay, maybe like directly show you how it works. First, okay, again, I have to insert something first. Okay, I create a, okay, one thing, this hash table must be in prime number. Yeah, later I will explain why it must be in prime number. So it must be in prime number. So let's say it's a 7. This one got 7 slot. I just insert. Then another one 4. I insert first. Okay, modulus by 7. No collision. So seems like quite okay. Then no collision. Just insert mod 7. Then just insert mod 7. Just insert mod 7. Okay, there's a collision. What should I do next to find the alternative location? They will use this increment. You need to know what is this increment. 11. Here I define mod 3 plus 1. I design in this way. Mod 3. So what is 11 mod 3? 11 mod 3, you get 2. 2 plus 1 means 3. Okay, so I will increase by 3 slot. 1, 2, 3. So I will go here. Still got collision. Yeah, you go from here, go to here. First step. Got collision, never mind. I go look for another, I will move another 3. So after that, I will base on the increment hash function, yeah, which is giving, yeah, is 3. So every time I will increase by 3. Yeah, so first time here not working, then I go to here, not working, then I will move 1, 2, 3. I will go to here. Yeah, just nice. It's an empty slot. So the good thing for this is you notice that the increment is this increment function, the hash function, is depend on my key. So that means every key have different increment function. So even your initial slot, you have the same slot, but your increment will be different, depend on your key. So every key will have different way to prompt the new location. So you won't that easy from any kind of a clustering, because every key have different pattern of search the new prompt new slot. Yeah, when the collision occur. Okay, so that's why double hashing will give you a better performance in terms of searching and insertion, because lesser chance to form the clustering. Yeah, you lower the chance of clustering, any form of primary or secondary. And then if you go and think about it, why it must be a prime number, because doing so, yeah, you find that, yeah, if it's a prime number, then you will ensure that plus 3 plus 3 plus 3 plus 3 or plus 2. If this thing is not a prime number, let's say it's an even number, what happened that my increment is plus 2? If it's plus 2, you will come here. Plus 2, you will come here. Plus 2, you will come here. Yeah, plus, no, this is not a good. This one got, okay, one more times. If my hash table is not prime number, it's an even, let's say is in this case, let's say I add one more slot, yeah, you will find that there's an issue. Plus 2 is here. Plus 2, you will go to here. Plus 2, you will go to here. Plus 2, you will go to here. If it is not a prime number, you have a problem. Do you notice that if my increment give me is 2, some key let's say I got some key, and my table size is even number, yeah, and the increment also some even number, then you have a problem. You plus 2 plus 2 plus 2, yeah, soon you will realize that the in this case all the odd slot been searched, but even slot, no matter how, you won't be able to prompt and go and check whether the slot is available. That will causing that you only check half of the slot, the availability of half of the slot. The other half, you have no chance to insert it. And you very easy that your table is not full, but your hashing method, you won't be able to insert the key, even though your hash table is not full yet. Yeah, so you need to make sure that your hashing can visit every slot. Your problem, it can be visit every slot. So that's why the hash table for double hashing must be prime number. Yeah. So another thing is this one. Why I need to plus 1? Because this thing can be returned 0. I also cannot be, my increment cannot be increased 0. Then you will stay in the same slot forever. Okay. So yeah, this is the double hashing. Yeah. And this one just for your information. I think it's beyond your capability to analyze. At this stage, I think I also don't want to go to the detail how to get this time complexity of all this linear probing and double hashing. But what I want to show you here is like, all of them are 1 minus alpha. 1 minus alpha. Is the function of 1 minus alpha, their time complexity. If you're interested about the proof, you can find this book, The Art of Computer Programming, by this genius, which is the Turing Award in 1974. Is also the father of analysis of algorithm. Is a very well-known person. You should know as a computer science student, you take algorithm, you should know this person because all this thing is proved by him. You want to blend today, you need to study all this thing is due to this guy. He's still around. He's a genius. I think he in 1973, when he are at the age of 35 years old, he already improved all this stuff. And in 1970, so these are the things he show you. Not I show you. Just let you know. So one thing what I want to show, one thing is the open addressing. Open addressing because you only have one hash table, the one array. So this thing definitely less than, or at most when it's full, less than or equal to 1 only. So this thing, what does it imply? 1 minus alpha. That means 1 minus alpha. At most 1. When your table is almost full, then your search complexity will increase. When you almost full, the search will be increased. Compared to close addressing, the alpha can be greater than 1 because using linked list. So your hash table, your n can be bigger. Your n can be bigger than hash for close addressing. For open addressing, it must be less than that. It must be less than or at most you can when it's full is equal to 1. Your alpha, your log factor for open addressing. Okay. So all this I show you here is trying to tell you that when your table is getting full, almost full, the time complexity will increase. Will increase very fast. So from here, or whether you use linear probing or double hashing, all have the same characteristic. Just a little bit different only. Maybe double hashing slightly better, but not really improve any too much. If you compare these two functions, you can see. Okay. The key I want to why I have to cover this because you're related to your coming assignment. Okay, you want to delete a key under open addressing. Okay, it's possible, right? You can insert, of course you need to think about delete, but it's not simply really physically delete the key. So that's why you need to put some marker. Then you have a hash table. This thing need to take notes. Later you see your assignment, there's one question asking you to do this. You got some key. 1, 2, maybe 5. You want to delete 5, for example. You cannot really physically delete it because especially open addressing, under open addressing, close addressing, delete quite simple. Delete, just remove from the linked list, no problem. But open addressing is not that simple because the thing can be 5 maybe earlier, maybe 1. No, this one. Let's say I want to delete 5. It cannot be simply deleted because maybe 1 earlier is start from here. Maybe when I insert 1, I insert is trying to from here, and after that I search. I prompt another new location here. Then I insert. If you delete 5, you will cause me cannot find 1 in the future. So to prevent such thing happen, we cannot really physically delete this thing. We only can put a marker to delete it. To set this slot is deleted and keep the things there. Yeah. So that means when you search, you still go to here, you find that there's a marker here. Then you don't need to do any comparison because this key is already deleted. Then you still can have that there's a possible in other location because this one previously something is there, just deleted. So my 1 can be in another location. I have to carry on my search. Yeah, so that's why when you delete a key under open addressing, you cannot simply delete it. You have to put a marker. Yeah. Of course, after a while, maybe really delete too many slots. Yeah, in the worst case scenario is you have to do this kind of garbage collection. In other words, you have to take out all the key and clean out all the things and reinsert again. Yeah, that is so-called garbage collection. Yeah, that means reshuffle all the slot, reinsert them. Yeah, to clean out the things. Yeah, when you delete, you have a large number of deletion. Yeah, are done. So that will improve the search. Because if you delete here, delete there, that's why every time you need to search certain thing, you need to prompt to a lot of location which is deleted. Yeah, also not very good. Yeah. So to improve eventually, when you delete too many stuff, you need to set some criteria that you need to, it is a time for you to do the garbage correction. That means you need to tidy out, clean out, do the housekeeping to clean out your slot and reinsert the key. Okay? Yeah. So another way also you need to do this kind reinsertion is like when like I mentioned, when the alpha getting bigger and bigger, you also need to, it probably also prompt you something that you need to increase your table size. Yeah, so a lot of time after the alpha may be greater than 0.5 or 0.7, we were trying to double the size. Yeah, and rehash all the key again. Yeah, that means you create you have a smaller table at the beginning when they are almost full. Yeah, when they are close to 1, close to 1, you will create a bigger one. And then one by one reinsert it again. So this thing we don't do very frequently because this one very time consuming. So normally and also we double. When we increase, we don't increase a little bit, we just simply increase 2 times, 3 times, 4 times. Yeah, so that we don't keep encounter this kind of rehashing problem. Yeah. So that is how the hashing work to achieve constant search time. Yeah, so overall searching we cover a few approach. One is the exotic algorithm, linear search or sequential search, which in the big OR. Then we also use the binary search on Monday, decrease and conquer, which achieve big O log 2n. Today we cover is the hashing. Hashing will take, on average, should be achieved in constant time. We're trying to make it in constant time. So the hashing table the hash function need to be well designed so that we can achieve constant time. And also we need to make sure our collision resolution, whether we are using closed hashing or open addressing hashing, we need to make sure that the searching time can remain in constant time or in alpha. That is what we always trying to do for hash table. And also hash table, you need to consider delete key and rehashing. If you want to delete the key. So that is all about the searching. And hashing I have to emphasize one more times because I expect in your assignment again the so-called the tips for your assignment 6. When you delete the key, you have to take notes the key comparison. Yeah, I have to emphasize when I'm talking about key comparison, that means there's some key comparison process happen. That's so-called key comparison. Yeah, when that means you want to search something, yeah, I ask you the number of key comparison. What is the number of key comparison? It's not you go and compare the slot. It's compare the key inside the slot. It's compare the key inside the slot. Yeah. If the slot is empty, nothing inside, there's no key in the slot, or not surprising, there's no key comparison happen. Right? Yeah. Because last year I got the experience. Yeah. People spend a lot of time to do the assignment. Yeah, they keep struggling this key comparison. I don't know why someone interpret key comparison is the slot comparison. Not true. When I said here key again, today I repeat many times already. I hope this thing won't happen again. Key comparison is compare the key inside the slot. If the slot is empty, there's no key comparison. Okay? That is today's lecture. Maybe any question, I see whether I can answer. The time complexity, talking about the hashing key to the hash table instead of retrieve the data. The hash, this one is probably, it's talking about the search time. I guess you're talking about this. Can re-explain what exactly we are storing? Is it we are trying to store some information? Well, and here all the example I'm trying to give is just simply insert just the key is just some integer number. Of course, I can make this integer number as some ID, and then this ID can attach some data. But in the end, all the searching, all the hashing is still just based on the ID, the index, the ID, the key to insert. Behind you carry whatever data, we don't really care. So here I didn't draw what data. Yeah, we only focus on how we do the mapping. You give me a key, you generate a key, the key map to the hash table. What the information you carry together, I didn't mention because that one wouldn't it does not related to the mapping. The mapping all rely on the key you generate. Can you explain how do you derive the summation expression in the okay, good. That is probably the one of the thing really need to think twice. Close one is here. Yeah, that one, yeah. This among these things, yeah, this one, I think starting all these things should be you can understand. I think this is the one of the very difficult to some people to visualize it. Imagine average. We're talking about average. That means the average. That means my hash table. Now I'm talking the closed hash address hashing. Average, that means they are evenly distributed. So each slot are evenly having a linked list have a average number. Yeah. So maybe some a little bit longer, some a little bit shorter, doesn't matter. Okay. Yeah, let's say I have some all my element are all in the on the all average case. Yeah, all elements are equally likely hash evenly into the H slot. Can I accept? Okay, this thing okay that's mean all the location have about the same number on average. That's mean on average it should be n over h. Yeah, on average, the distribution each linked list, the size should be alpha. On average should be N over H. On average. Yeah, but it may, the thing is that on average, I'm saying on average not mean that every, definitely is N over H. On average, they are N over H. Okay, so now you are talking on where. Okay, so no, I believe that should not have any issue for unsuccessful search. The time complexity on the unsuccessful search. Unsuccessful search, you give me a key, it's not there. Unsuccessful search, you map to any slot, whatever this key after the hash function map any slot. On average is N over H. So the unsuccessful search, the time complexity is big theta alpha for unsuccessful search on the average case. Agree? Where is the person? I think it's who asked me this thing? Can you explain the summation? Yeah, Nisi Mono. Okay, I hope you can get it. Then next one is the something you need to think. What is the successful search? What is the successful search? Successful search. Today I want to search the I item. I got N item right in the hash table. The I item. Particular item. What is the time I need to take to search that item on average? I item. I item can be in any places. My table can be my table size. All those on average, I said on average equally likely is N over H. But some may be long, some may be short. You don't know. It's just trying to set on average is N over H only. They didn't set that must be N over H. Okay, on average only. So can be one element, can be two element, can be three. So many combination. What is the successful search of the I item? The trick is behind is like that. You imagine you haven't insert this I item. Okay, so that means before I can search the I item, before this I item, so you take this thing out. Imagine that you haven't insert the I item. That also implied that the I plus 1, I plus 2, I plus 3, I plus 4, all these items have not been inserted. So imagine that, change another color. The table before that thing happen is something like maybe a little bit shorter. This one got 1. This one maybe already have 2. This one is 1. Something like that. It's something like this kind of table. The I item have not been inserted. Maybe this one not here lah. Imagine this one not here. A little bit smaller table. Okay. Then so the successful search, that means is like I am trying to search this particular I item in this table first. Unsuccessful. Then the I item somehow insert it somewhere. Then I found it. So it's like before the I item is insert into the hash table, the average length of the all list is I minus 1 over H. So here is before I insert is I minus 1 over H. There are so many items, I minus 1 item, in the hash table. So average the search all are unsuccessful because I item is not there. So for sure you unsuccessful one. So this one will take, so when so the number of comparison on average, you're trying to search in this scenario, in this blue color scenario, you have I minus 1 over H item inside. I item is not inside. I item I haven't insert. At this moment. So all your search, when you're trying to search the I item, definitely you fail one. Yeah, so what is the average time complexity to search the I item here? So which is, you will take so much, already tell you earlier. Unsuccessful search, you won't be able to search that thing. Yeah, that I item. So that will take so much. Yeah. So now the thing is like, what is the successful search for I item in the red color? Yeah, so this one should be, this one unsuccessful. After I insert that one, then I found it. Yeah, on average, +1. When the I item is sought for, the number of key comparison is I plus I minus 1 over H. Yeah, no matter this I item is where is it? Yeah. So on average, this I item, because they're not trying to talking about one scenario. This is just example. They're talking about on average, all kind of a possible combination. Yeah, how do you analyze all kind of a possible combination? Yeah, so it's trying to, yeah, no matter how you search the I item, is before on average you search through the I minus 1, not, yeah, before you insert that I item. Yeah, those things are already inside the table. Then, yeah, you're trying to search them on average, you're trying to search this item on average, unsuccessful. Okay, then the next step, you found it. Because the next step is this I item. You found it, so you need to +1. Yeah, so that is the complexity. Then you also need to consider I is the first item, second item, third item. You got n item, so you need to think about it over n item. Yeah, so that is what I mean, n item. Yeah, this is the n item. So you need to consider the first one, second one, what happened. So every cases you need to consider. I think the derivation is here. So the derivation is here. So you need to consider I equal to 1, I equal to 2, I equal to 3, 4, 5, 6, 7 to n. Every cases on average, every item. Yeah. Then this is the average. Yeah. I think the rest you should be okay. Yeah. Actually, this is just the last term. Only the last one. This one is the arithmetic series. Yeah, I already showed you earlier. Yeah, then this one is n. Then this one is 1 over n. Then you just simplify it. Then you find that is 1 plus alpha. Okay. Then let me see who else. Can log factor of close address be? Can. When your n item less than that, close address, yeah, is n over h. Yeah, n can be 0, n can be 0, n can be infinity, n cannot be infinity. Definitely you need to have a finite number. But can be any number, right, for close. Because linked list, linked list, theoretically, I can store arbitrary number of data, right? So, yeah, although your h is fixed, the table is fixed, but behind it, the one connect to him, the linked list can be arbitrary size. Yeah, so n can be alpha in the close addressing, close address hashing. The alpha can be from 0 to, theoretically can go to infinity for close address hashing. For open one, definitely cannot be more than 1. Anyone else? I hope no. If no more, I will stop today. Sorry, today a bit overrun a lot. Sorry. I think earlier I starting need to clarify something. Yeah. Why do we need to consider from 1 to... Because you got n item. I need to take the average. Yeah, you need to consider every cases. Yeah, just now the explanation is only one I item. Yeah, you need to consider your I item can be first item, can be first item, can be second item, can be third item, can be fourth item, can be n item, because in your hash table there are n item. You need to consider every cases. Yeah, the first insert item, the second insert item. For example, the first insert item can be insert in the first slot, can be insert in the second slot, can be insert in the third slot, can be insert in the fourth slot, and so on and so forth. The second item can be insert in the first slot, also can be insert in the second slot, also can be insert in the third slot, and so on and so forth. So sometimes can be item 1 insert in the first slot, item 2 also insert in the first slot. Yeah, then they become 2. Yeah, then, yeah, that's why I said average case, there are a lot of combination. Yeah. So how to analyze it? Yeah, that is unsuccessful case, quite clear. Successful search, you need to think about it. It's a bit tricky. It's like you imagine you have not insert that item first. Then what is the average search? Then plus one more search, you got it. Oh, so we considered the search time for every single n and every combination. And then divide by n. And divide, yeah, I item here, I divide by n. Yeah, all the possible scenario, all the possible item. And yeah, that's why. And all the item have an equal chance to be searched. So that's why it's 1 over n. That's why here there's a 1 over n here. Why is 1 over n? Because each item have equally likely been searched. Okay. Any more question? Anyway, if not, I think you still can send the email or seeking consultation or whatever way lah. Okay. I will release the assignment 6 probably tonight, I hope. Yeah. How to choose hash table sites for close address. And this one not really have any special issue. I don't see there's any issue. Yeah, the sites can be, because behind the collision, the open addressing need to select the sites carefully is because you're probing. This one is all linked list. Collision is not an issue one. Yeah, so I think the sites for close addressing not too big issue. Yeah, you can depend, you need your requirement to choose. But the key is your hash table. Mainly is depend on your, probably is highly depend on your hash function you select. Because earlier I already said that select the hash function. Yeah, you sometimes like this one. The real data, your hash table, whatever is open or closed, this one should be trying to select as a prime number and not too close to any power of 2. Okay, I think the number is start dropping. Should be everyone go for dinner. I also need to go for dinner. Okay, goodbye.